Business Development Manager for terminal units and fan coils.
Business Development Manager. That's a mouthful. So I've known Mark for a handful of years now, and we always have interesting conversations about the development of different price products. He's been leading the way on a lot of the innovation for price, not only to have, part of our subject today is dealing with lower water temperatures, but also with duct leakage, constructability, manufacturing efficiency, all that kind of stuff. So Mark's a great resource. And aside from Mark, Suthan from our office is going to be wrapping up the presentation today, the last half an hour, showing you a few tools that you can use to save yourself time when you are picking these terminal boxes. So without further ado, I'm going to turn this over to Mark and put myself on mute, but please feel free, or no, let's not say feel free, please use the Q&A. We'll be monitoring it. And you can also, I think, send a chat message. So looking forward to hearing what you have to share with us, Mark.
Great. Thank you, Tom. And thanks to everyone for joining. It's great to hear, this is our highest registration yet for an airflow session here, which is awesome. I think you guys should feel kind of special, so to speak, in the chat. I was admitting to Tom before everyone started hopping on here. One of the products we're going to discuss today has been market tested with a few engineering firms. It's been a near and dear to my heart skunkworks project for kind of the last 2 years. But this would be kind of a more official public unveiling of the product, which is exciting. And so looking forward to, in follow-up, hopefully hearing some feedback from everybody. Feel free to weigh in once again in the Q&A or in the chat. I'll be monitoring both of those. And we're kind of off to the races. So a little bit about me. I am a Canadian currently living in Atlanta. So as I noted, for anyone who'd already hopped on, my first American Thanksgiving this year. Thanks to the Airflow and Price marketing team for making me look very cool in this Thanksgiving snapshot here. I will admit I'm a ham fan, not a turkey fan. I know that's a hot take for some, but I think turkey exists only at Thanksgiving and Christmas for good reason. It's complicated to cook and doesn't taste all that great. My bad.
A little bit of a turkey neck here too, Mark.
Yeah.
Unfortunately, that was intentional.
They did a pretty good job. I don't think technically the neck is fully anatomically correct here, but I'll let that one slide. So my history with Price began in 2015. I was an R&D engineer doing acoustical testing for products, product development. I did a lot of product development at that time for kind of our series fan-powered terminal line for our fan coils we were developing at that point in time. And I worked in the lab for about 2.5 years and loved that. And then I had about a 8-month stint as a product designer. And I kind of thought and envisioned I would be a design engineer until a role with application engineering opened up. And I think I spent too much time talking around the office and not enough time CAD modeling. So I quickly kind of got shoved over to there, managed that team for a couple of years. And then in November of last year, I relocated to the US to kind of lead strategy and development for 2 of our product categories at Price, our terminal division and our fan coil division. All of the AHRI certifications, which we're going to discuss today, what those are and why they're meaningful to consulting engineers. But all of the certifications for Price product for AHRI, I'm kind of our voting sitting member, whether that's water coils, terminals, fan coils. And that's an important part of this conversation. So we'll talk a little bit about those standards today as well. This is a pretty heavy content presentation from a technical perspective. So please be active in the chat. Feel free to ask follow-up questions. I'm going to be monitoring that live. And it's technical, but it's important. And so I'm hoping we can kind of tell the story and lead our way through this, starting from the discussion of space heating broadly, kind of what market trends are informing design decisions. We're going to talk, about specifically single duct heating. What are some of the market constraints that are informing single duct market dynamics as well? And then we'll kind of move into product specific, content. And from that, we'll go into new products, both our low water temperature coils, which we actually released yesterday, into our selection software for our reps, and we'll quickly be releasing into our selection software for engineers, our Excel toolkit, and kind of the whole suite of price products. And then we'll talk about a new patent pending single duct unit to close. So a bit of a roadmap there, but starting off with market trends impacting space heating. This is my opportunity to stand upon the pulpit and discuss decarbonization like everybody else in the HVAC industry. But to be honest, I think it's an important piece of context because it's leading to a lot of development of new, interesting product, whether we're looking at, new kind of better boilers or heat pumps, or, even improvements when we look at chiller technology, heat recovery chillers. And the reality is it's because the built environment is responsible for a huge chunk of carbon dioxide emissions. We're probably not going to change global warming by using paper straws. It's probably going to take bigger equipment and larger infrastructure. So I think the built environment is under scrutiny, and I think it's worthy of some scrutiny because 40% of those emissions come from the built environment, and then in particular, heating buildings is a huge component of that as well. Of course, we need warm buildings. As a former Winnipegger, I stand kind of in solidarity with all of you cold climate folks. Of course, we need warm buildings, but if we can do it more efficiently, that's a good thing to try to do. And so how do we actually influence and see the built environment become more efficient over time? Well, I think the biggest way is through energy code adoption, ASHRAE 90.1, and its influence on the built environment. So the big takeaway here is when we look at ASHRAE 90.1 historically, it's continually gotten more and more and more efficient. ASHRAE 90.1 2022 is nominally using about 60% less energy than a building built to ASHRAE 90 1975 or 1980. So we continue to see energy code require improved efficiencies, and then we continue to see localities adopt newer and newer versions of IECC, which is referencing back to 90.1. So when we look at the design paradigm in Wisconsin, currently we're kind of living in the 2013 ASHRAE 90.1 paradigm. When we kind of roadmap and look forward, maybe 3 more years, that's going to probably shift again. 5 more years, it's going to shift again. And that's going to lead to new design philosophies and new product types and new systems being used to comply with those building requirements. Another big piece, and when we specifically think about heating, I think we need to consider where is our heat source actually coming from. And this is the conversation of potentially electrification. It's also the conversation of renewables versus carbon-based fuel sources. And so this is from a McKinsey & Co. study from July 2022. And their focus here was looking at actually how heat pumps can help decarbonize the built environment. The one thing I really like to flag here, I think a lot of this stuff would be clear to everybody. Of course, a heat pump, whether it's ground source or air source, is going to consume less energy. Therefore, it's going to have a lower carbon dioxide emission rate than, say, a natural gas boiler. But when we look to kind of moving towards all electric as a solution, I think the next step is, where is electricity actually coming from? So this study focused on the northeastern United States, but the irony of, moving to an all-electric building is that can actually be potentially a higher carbon dioxide emission building, depending on where that electricity actually comes from. And when we look at electric resistance heating, it's a great solution, but it is limited by a maximum COP of 1. We can get heat out for electricity in. When we start to look at different solutions for heat sources, like air source or ground source heat pumps, of course, that efficiency can be much higher. And, it can also be an electrified solution. So my broad global takeaway on, what I see as the trends for heating systems, and in particular hot water supply heating systems, is we're continuing to see more heat pumps being used as core heat sources. We're even seeing, conventional boilers not really used for new construction anymore. Now it's a condensing boiler. That's the status quo. We think broadly at price that we're going to continue to see hot water supply temperatures trend down. The 180-degree system for a hydronic heating system of the past is becoming a 140, is becoming a 120. In some markets is already existing in a 115 to 95 degree. And with that, we get a lift in coefficient of performance for those heating systems. The lower the hot water supply temperature, generally the greater the coefficient of performance as well. So some key takeaways or thoughts for this first section. One thing that we know generally now in the United States, hydronic heating is emitting less carbon dioxide than electric heating. That's true currently. Hydronic heating is consuming less electricity than electric heating because of that elevated COP that we can maybe get from ground source heat pumps. So that's a potential lever to pull and a trend that we see. Generally, the lower the hot water supply temperature, the more efficient the system. And then a peek behind the curtain, I can tell you guys over the last 3 years, I see a terminal unit sales shift about 2% annually per year from electric reheat shrinking to hot water reheat growing when we look at the proportion of those two different options being used. So hydronic is increasing in its growth rate. The expected outcome here is we should see more hydronic heating, especially I think in colder climates. So I think for Wisconsin, that's definitely true. And, I'll continue to expect to see a decrease in that hot water supply temperature over time.
Hey, Mark, I was just wondering if you wouldn't mind interjecting. So in Wisconsin, I don't believe we do see all electric buildings, but they're all electric, as in it's a rooftop with an electric heating section, electric baseboard, electric VAV boxes. I am aware, but I don't see heat pump, central heat pump buildings. That's not true. I guess we do have geothermal systems that does exist. But are you seeing, where are you seeing central heat pump systems being built? Is it all the East Coast? Is it just government buildings? What is your, and what are you seeing for colder climate states like central heat?
Absolutely. I'm gonna, just to give us a bit of a backdrop to address that, because I think it's an excellent question. I'll jump ahead. We'll see this slide later. But I think broadly, when we look at climate zones 5, 6, the challenge is the air source and the ground source heat pump is not really built for the environment we're existing in. And that's because, looking here at like the Ascend from Trane, a very hot, very kind of popular air source heat pump. When we look at the ambient temperature, our hot water supply temperature quickly decreases for this air source heat pump when we also look at our ambient temperature decreasing. And we're essentially at the wrong end of the relationship between ambient temperature and hot water leaving temperature, because of course Wisconsin on design day in the winter is cold, so that means we need more heat, but it also means we get less temperature. So I agree. I think geothermal is an opportunity that will grow in cold climates. I've seen more geothermal in some Midwestern markets. Geothermal is actually an extremely popular option when we look at Winnipeg, Manitoba, and Canada. So we can see it work. Of course, we get into the civil side of engineering. What's our soil type? How does that impact things? It becomes kind of a ballooning problem. I expect when we look at, Wisconsin, when we look at Minnesota, we'll see the utilization of condensing gas boilers for longer in those markets. I do think we see more innovation, though, in product development on the heat pump side, which is rapidly expanding the kind of relevant markets where they can be used. So 5 years from now, there'll probably be heat pump solutions that can actually be used and leveraged in Wisconsin. So it'll be a trend everywhere. We're probably more in the natural gas boiler paradigm for a while longer in Wisconsin, which fortunately is really all of this presentation. So great question. And I haven't seen any questions in the chat yet from our attendees here, but still, I will monitor. And no, you guys can ask me anything. So
come on now, participants, let's see some Q&A.
Beautiful. So moving on to market strengths impacting single duct heating in particular, obviously we need to start with a little bit on single duct systems. When I think of multi-zone commercial HVAC systems, that's kind of synonymous with single duct systems in a lot of cases. A single duct is letting us have zone-specific comfort and indoor air quality. It's going to improve the overall system efficiency in many cases because we can measure and control and regulate specifically to the needs of the individual zone. The kind of three major pieces from an air distribution perspective: we have a package rooftop or an air handler, we have single duct terminals, we have air outlets. And, very frequently this is using hydronic or electric heating coils, especially when we look at the market that you guys do business in. So my one other high level piece, when I just want to give my pitch on a hot water reheat coil, of course, we have cold, saturated 55-degree air for design day coming into the single duct box. We're going to need to reheat that air or heat that air to 85 to 95 degrees to be able to actually address, the heating requirements of the zone. And when we look at the water temp in 180 to 100, water temp out, we're generally trying to get, some kind of delta T of 15 to 35, maybe 40, depending on the core system we're using. One thing that I really like to note for single ducts is, of course, they don't really have like a coefficient of performance. When we think of this heat exchanger, it's a heat exchanger. All we're doing is exchanging energy from water to air. And, if we do that more or less efficiently, we're not losing that energy. It's just going back to the boiler or back throughout the system. So that's a consideration which is going to influence and impact some of the discussion we have in this presentation. So something that I wanted to flag. Now, when I do think of marketing constraints or market constraints for single duct units, I think one of the most important things that we all can agree, even me, it hurts my soul, but it's true, we're dealing with commodity product. Single duct units over time have been widely commoditized. This is one of the few slides that I would ever put competitor products, in one of my slide decks, but I think it's interesting to see, 6 different single ducts here. If I could ask anybody if we were in person, I'd say, guess which one is the price box. I doubt many of, people in the room would get the right answer. We kind of have a 1 in 6 chance. And the truth is, this is commoditized product. We see about 500,000 single duct units sell annually to the North American market. And generally, these products are fairly standardized and generally indistinguishable from different producers. When I think of a contractor and their view on it, I think that's especially true. This is a pricing driven market, which has its pros. I think, competition drives down equipment pricing. That's a great thing for building owners. That's a great thing for contractors. Also, we see a lot of consistency in mechanical design, scheduling, and specifications, which I think is also really great for the consulting engineer. But there are some risks with a highly commoditized market, and that's lack of manufacturer or industry innovation, which we'll talk a little bit about. We don't see single ducts change as rapidly as some of the products that are more engineered, because there's a business incentive to quickly change in an engineered market that's less commoditized. The other thing we can see in the cases of some manufacturers is actually, I would say, reduced product quality over time. And that's because the market chooses the price broadly for a commoditized product. And manufacturers are kind of fighting tooth and nail to try to protect that margin over time, which I think can lead to poor quality product in the case of some market competitors. We'll talk about how price treats that and kind of our view on that in the next section of the presentation. The last thing I wanted to note, which is just cool data that I measure over time, but looking at the North American single duct unit kind of market in the top right of the screen here, we can see single ducts with heat are actually very stable over time from kind of 2015 till now, while single ducts without heat are a trending down market. So the cooling only single duct box is kind of trending down as time goes on. Single duct with heat is generally much more stable. And here's my opportunity to talk about the industry. And I think, this kind of leads to some of the drawbacks of a commoditized market. The industry and our standards become kind of commoditized as well. And so standards and certifications influencing single duct boxes, there's two pieces to this pie. There's the ASHRAE side and the AHRI side. And I want to draw some distinction between the two. They're kind of two halves of a whole in many respects. ASHRAE standards really care about the design and operation of the HVAC system. They're caring about indoor air quality, indoor environmental quality. They're caring about energy efficiency. When we look at AHRI standards, this is about products. So product-specific performance ratings, standardizing testing for product, and trying to really encourage integrity within the industry, making sure all manufacturers are providing a minimum viable product to the marketplace with some version of control. And so when we look at water coils, we have ASHRAE standard 33 and AHRI 410. When we look at terminals themselves, we have ASHRAE 130 and AHRI 880. And the really important standard for us to discuss and talk about right now would be the AHRI 410 heating coil standard. So this is the performance rating of forced circulation, air cooling, and air heating coils. And this is kind of the scope in which manufacturers play when we think about developing, innovating, creating new hot water coil product. And there's a lot of benefits to this standard. It makes sure that manufacturers have accurate performance. So when we look at a product that's certified to this standard and audited to this standard, capacity needs to be at least 97.5% of what we say it will be in our catalog. And they're going to audit and check this every single year. Pressure drops, whether that's air side or water side, must be less than 105% of catalog. They will audit and test that every year. They also create and constrain the way that we test and the way that we acquire data. So there's minimum viable data acquisition and testing procedures, and it makes sure that manufacturers, have integrity and consistency. But this standard is large and it's complicated.
Mark, I just got to say this when you shared this the first time around, this is just mind-numbingly surprising. We only test the one I'm sure there's every lab that tests terminal boxes has the ability to test to a different temperature other than 80, but somewhere along the line, someone said, we're good, 180, all done.
Exactly right. Yeah. So a great comment from Tom on the drawbacks here. And the truth is, this standard is not only hot water coils, it's water coils, there's DX, there's steam, there's refrigerant, and then there's latent and sensible cooling. So it's a wide breadth within the standard. And then when we kind of focus in on any particular product segment within there, it's pretty high level and there are some drawbacks. So hot water coils are tested at 180 degrees only. Hot water coils are also not tested installed on equipment. So that means the catalog data you see for a single duct hot water coil, it's installed in ductwork with perfect uniform airflow. It's not actually installed within the terminal itself. I will say, as a voting member of this standard, innovation is pretty limited. There's a ton of manufacturers who have representatives on this standard, and it's hard to get punctuation changed, let alone full new versions of a test added in, at least with pace. And I would say most manufacturers look at the testing cost and scope and really don't want to see that scope creep over time. So the questions I would ask to the market, the questions I would flag to the standard committee is, well, are people's accuracies for hot water coils changing at lower water supply temperatures? And what happens when that water coil is actually installed into equipment? What happens if it's right downstream of a damper that's almost fully shut? What changes? And so those are the questions I think consulting engineers need to be concerned about too. And those are the questions. I'll dangle this. We're going to answer those later in the presentation.
Just curious. This is not limited to terminal. This is just coils. This is not the air handling coils. This is fan coils. This is all coils. So maybe
Correct.
in the grand scheme of things, the terminal box coil is, from a BTU sense, a small increment, but still over every part of the building has it. But boy, your air handling coils are only
So
just
it's interesting. And what I would suggest, is that terminal units should have a broken out standard that references back to 410. In the same way that actually fan coils have. So fan coils have AHRI standard 440, and all fan coil coils get tested within the product. So there's precedent for it in other product segments in the market, but there is no version of it specifically for terminals to do the same thing currently. So maybe that'll change. I hope it will. And we'll chat a little bit about that. So I do want to talk about, I made a couple bold claims. The first is a commoditized market means there's little innovation, and it also means that maybe product quality deteriorates over time. I'm aware with saying that, as a commodity manufacturer, that maybe raises some flags. So I do want to talk a little bit about price and how we innovate within a commodity market and why that's important to us. And one of the big pieces for that would be a very under the radar, massive engineering effort that our reps know well, but generally the consulting engineer wouldn't have heard too much about, which was the release of a fully re-engineered single duct unit casing and assembly method in September of this year. So we spent 2 years, we spent over 10,000 engineering hours focusing on making it really more optimal to produce single duct units. We're the single duct market share leader with about 40% market share. We ship products from 5 different plants to all over North America. And we spent about $150 million of capital investment for new equipment and fully redesign the product to really improve construction efficiency and to reduce the assembly time of our product. Now, what did we do? Why did we do this? And what does this look like? Well, in some cases, it was speed and quality. So we want to be able to offer 3 and 4 week lead times on a product class that, many other manufacturers would be 5 or 6 weeks. We wanted to improve operator safety. There was some old operations that we viewed we could make safer for, our factory staff to actually assemble the product. That was a huge component of it. And we wanted to reduce footprint for manufacturing as well. A good example here, the old single duct casing, we'll look at the lock form version of it previously, had 4 different operations on 4 different machines. We consolidated all of that down to a single operation on a single machine, which means new floor space for new lines so we can produce more product. So lots of benefit there. The other truth is we're aware that we don't control market price for this product. And so we do see our margins deteriorate over time. We make less money on each single duct sale. We don't want to try to reset the market price or suddenly start charging more. So that means we're just going to get better at building it. That's how we're going to protect our return on sale for these product classes. So with this, we had a bunch of positive byproducts of the new design as well. I spoke about this in another airflow session, and I'll speak about it here again. We realized we could make a lower leakage terminal while also making a terminal that's faster to build. So the left is that lock form hem-locked construction. We can see we would have 2 different pieces of sheet metal, the blue piece and the green highlighted piece that would be hammered together with a mallet with a classic lock form style of mate there. Where our new construction is screw assembled. It has better leakage performance, and it also has the opportunity to easily gasket those seams, which from an operator perspective is pretty simple and allows us to improve leakage even further. So I'd shared this in our previous airflow presentation on leakage, but we can see the Price Industries kind of old performance, that light green line. It's maybe a little bit hard to see with some of the colors here, but we were kind of top of what I would view as acceptable market leakage. We like to be first rather than second or third. So with the new design, the dark green, you can see we did have incremental improvement on our leakage rates for these single duct units as well, which is a nice benefit. And of course, one that Tom loves to talk about, because what is the cost of a leakage, CFM of leakage? Fortunately, not an answer that many people in market have a good response to, but it is something that certainly impacts and influences both the comfort of buildings and the operating costs of buildings. And when we look at decarbonizing and electrifying things, why are we dumping air into the plenum for no reason? Not an ideal.
Well, let's get AI to start working on this instead of writing more blog copy for me. That would be a nice little job for AI to figure out what the cost per CFM would be.
That would be bad for the broad Wisconsin market, though, because everyone likes your marketing content so much, Tom. I don't know.
Yeah. Well, we got
to keep it pumping out. Another thing which came as a byproduct of this new release was we did a lot of testing outside of the scope of the classic ASHRAE standard. And what we noticed here with this scope is we actually have a cross-flow sensor that can measure much better than most other manufacturers in the market. We wanted to leverage that to help improve both design and build for contractors and engineers. So what we can see here is the actual airflow measured in our laboratory, and then the cross-flow sensor airflow are these 5 points throughout the range of an 8-inch single duct box here. And what we found was even with an elbow directly on the inlet, we were actually plus or minus less than 1%. With an elbow directly on the inlet. So we did a ton of testing to quantify this, and we actually have updated our documentation. So our IOM now states, hey, ASHRAE likes 3 duct diameters. We'll take 1.5 or an elbow directly upstream, and we'll still have plus or minus 5%. So, some other incremental improvements there, just because we had an opportunity to do a lot of testing on the product, and we decided to kind of push the limits of our equipment a little bit. A question from an attendee as well here, just referring back to the previous slide on Naylor's casing leakage here. It's kind of hard for me to fully comment on that. I will note what we're looking at data-wise here is competitor products purchased off eBay, a bunch of them, and a ton of testing in price laboratories to try to benchmark ourselves against competitors. So this is the data we see. We see their specification for their standard product is also at an elevated leakage rate. I don't know what the business choice is on their end. This is the data, and that's kind of as much as I can say. Generally speaking, we see pretty similar leakage performance from most manufacturers, but they were the outlier in the case of the testing we had performed in that case. Another piece of innovation here, one that might be interesting to market.
I'm just going to interrupt you real quick, just because there were a couple of percentages there that went by pretty fast that I noticed. So if you could go back 2 slides, just this 5, we're looking at the percentage of leakage here, just to make sure we don't get out of sorts, this percentage of leakage casing. And then in the next slide, Mark is talking about the SP300 flow sensor, which is a percentage of airflow. Just happened that those 2 slides were pretty adjacent, plus or minus 5%. So
very good point there, Tom.
Looking at an airflow flow difference. So just a couple of things that went by pretty quick. Sorry to interrupt, Mark.
No, thank you, Tom.
Not that sorry, be.
So, one last piece of innovation that I'd want to speak to here when we look at single ducts. Many of you might see on, a lot of the commodity terminal manufacturers that a valve package is now an option that many manufacturers can provide. We were also kind of the first to innovate in this area in 2018. It was actually work we were doing for Ford Motor Company that they had wanted, pre-construction for hydronic valve trims in factories to improve really construction throughput and to yield some better quality. Another good example of us trying to kind of push the needle forward, and generally, the market catching up and a lot of other manufacturers having this option as well. We are sourcing from 3 different valve OEMs at this point with IMI, Hydronic, Nexus, and Victaulic. We're going to continue to release this as a new option on a variety of products. But one thing that I'd like to note here, and another good example of maybe the price industry's pricing strategy, when we were first learning how to do this, it was complicated and expensive, and we've gotten a lot better at it. And in our view, of course, we love to make money, but we also like to provide innovative products to the market. And so this is a product option that as time has gone on and we've been able to build it more and more efficiently with higher levels of quality, our pricing is actually reduced, and we've cut the pricing to offer it to market at a more competitive price point as time has gone on, which is certainly something we like to try to do at price whenever the opportunity presents itself. So I'll pause there just for a moment. If there is, any questions, now would be a good time to ask. I'm kind of moving from the background portion of the presentation into more of this new product discussion, a little bit more into technical content here, and specifically discussion on VAV reheats, boiler types, what is the product selection that we need to do when we have different constraints of hot water temperature supply and different boiler constraints as well. And through this section, I'm going to have this same graph and table on screen populated with different data, but I wanted to take a moment to kind of parse through this table because it's going to pop up a variety of times, and I want to make sure everyone's kind of clear with what we're looking at and what the purpose of it is. Because I think that adds to the presentation quite a bit. So what this is, this little, presentation table here, this is the ASHRAE Handbook of Fundamentals Classic Single Duct VAV Reheat Schedule. And what we're going to always have is size 6, 8, 10, and 12 terminals. That is representative of at least 80% of the single duct sales sold to market from all manufacturers every year. For us this year, it's 83% of the single ducts that we've sold have been those 4 sizes. And what we're going to see this schedule being set up as is 2,000 feet per minute of maximum inlet velocity, which is the ASHRAE Handbook of Fundamentals Classic CFM for a VAV box. And it's also the AHRI certified ratings point, essentially where they test our product for pressure drop, sound, all of those great performance characteristics, which you populate into schedules. And 2,000 feet per minute is an important number because above 2,000 feet per minute, airflow has self-generating noise as it moves through a ducted system. What we're going to see is airflow becomes so turbulent, it kind of moves above a certain Reynolds number threshold that air pressure drop starts to get out of control, acoustics start to get out of control, and airflow measurement and control can be influenced and impacted in some respects as well. So 2,000 feet per minute is an important number. And when we look at reheat is limited by ASHRAE 90.1 to be 50% of our design day cooling supply airflow rate. So generally speaking, we are going to see reheat being 50% of those values. That's what we see in this column I'm highlighting right here. So this is 1,000 feet per minute of inlet velocity, and that's going to be consistent throughout the presentation. A few other things we'll note. I'm assuming a 55-degree supply saturated air temperature from the air handler. I'm assuming that we're going to be targeting somewhere an 85 to 95-degree supply air temperature for heating. ASHRAE would indicate to us 85 degrees is ideal so that we can avoid stratification within the space, which is going to impact our air distribution effectiveness and the volume of ventilation air we need. And then I'll call out on every table, what is our hot water supply temperature? What is our leaving air temperature? Kind of what is the target here? So with that being said, the first thing I want to discuss is conventional boilers. And I like to address this one with a question. So I'm going to ruin the Q&A chat for a moment here. But the quiz question is, what supply and return water temperatures would you consider are most typical for conventional boilers? Right into the chat or right into the Q&A section. We have item A, B, C, and D here. What do you typically see as most common if we're looking at a conventional natural gas boiler? I already have a couple answers rolling in here. 180, 150 or 180, 160 is kind of what we're generally seeing. So Jason, Heidi, Tyler, thank you. We're seeing answers coming in here and everyone's kind of agreeing A and C generally is what's most common. I agree. So 100% answer so far from everybody. Generally speaking, when I look at schedules from across the United States for single duct VAV systems with conventional boilers, we're usually seeing 180-degree supply and 160-degree return. 150, of course, is possible as well. But what is very critical for a conventional boiler is the return water temperature must be greater than 140 degrees Fahrenheit to avoid latent heat transfer of the flue gas on the heat exchanger inside of the boiler. If we're going to start to see latent heat transfer and acidic condensation being generated within the boiler, that is going to actually be a huge risk for the boiler that could deteriorate and eat away at the metal that the boiler is made out of, because generally it's not made to be stainless steel corrosive resistant. Now, the outcome of this type of boiler is a COP limit of 0.8 or 80% efficiency. And I think a great proxy for that is our exhaust air temperature. These boilers have generally a very hot exhaust above 300 degrees Fahrenheit at design day. And so what we're going to see is with hot exhaust, we see a limit of COP and we see energy kind of lost to the environment in that case. So our first view of a kind of fully filled out table here. The big thing to know when we look at a conventional boiler and we look at ASHRAE fundamental design conditions, a one-row VAV reheat coil was designed for a conventional boiler. What we have here is our 6, 8, 10, and 12, all targeting an 85-degree leaving air temperature, which is what ASHRAE would suggest is ideal. We have a one-row coil, and if I take the mass average of these 4 single duct units, our return water temperature is almost bang on 160 degrees. So when you think a conventional boiler application, what we most frequently see scheduled and specified from engineers? A one-row coil. What was the one-row coil made for? Exactly that system type. So maybe that's a little background from the manufacturer's side, but some context there for everyone to consider. I'm also going to pause here because this is a really good question that kind of relates to this table from Jonathan in the chat. So thank you, Jonathan. And his question is, in regards to airflow measurement and control, can price single duct VAVs provide constant airflow at 20% of design airflow? So 20% of design airflow kind of existing at 360 to 400 feet per minute. If our maximum supply airflow rate is 1,800 to 2,000 feet per minute. And how is that influenced by different product options? So from an airflow measurement and control perspective, yes, we absolutely can. If the correct type of controller is specified, DDC controller is specified, we can usually measure as low as 250 feet per minute. That would require static pressure reset to be utilized as well, because we need to make sure that the damper doesn't get too cut and too closed. That's a lot of information there, but hopefully I'm answering your question, Jonathan. I think it's an important one. The other question was, what about electric reheat and how does that impact things? In some cases, 20% of supply airflow rate could be a risk for electric reheat, just to make sure both thermal resets and safety circuit options, as well as airflow resets, are triggered and working correctly. The rule of thumb that I would generally recommend on that end would be, as long as we have 70 CFM per kilowatt, we're probably going to be existing in a healthy range for the electric heat to work properly. That could fall outside of that 20% limit in some cases, though, and that would be a good consideration to assess.
Maybe that'll be your next control strategy, is electric reheat for lower airflows on electric heat, but maybe in a year or two.
We have some irons in the fire on that too. I think there may be more 26 release options, but plenty on the works internally on our end, things to optimize for electric reheat as well.
Yeah, thanks, Jonathan.
So moving to condensing boilers, once again, right into the Q&A panel here. My same question, but in the context of condensing boilers, what is most typical for a condensing boiler system? We have A, 140 to 120, B, 120 to 100, C, 140 to 100, D, 130 to 100. I'm seeing some A's or B's. Randy's saying A, Armando saying A or B, Nick saying A. So some good answers there. I'm seeing a C, which is from Jonathan. And so I will say, more variety in the responses here. And I think that makes a ton of sense because we see these systems being leveraged and used differently. Now, I will note, when I look at most schedules for single duct VAV reheat, I frequently see 140 supply and 120 return. Now, this is one of my biggest flagged takeaways. Please don't do that. I want to talk about why, but please don't do 140, 120. And the reason why we don't want to do that is because of the way a condensing boiler actually works to improve its efficiency. What we're doing is we're forcing the condensation as much as possible. We want this boiler to condense. When we look at a greater rate of latent heat transfer and more condensation accumulating within the preheat section of this boiler, we are going to see more energy transferred from that flue gas to the water. We're going to see a rise in COP, and we're going to see, once again, our proxy exhaust temperature out of the boiler dramatically decreasing from 300 down to as low as under 100 degrees Fahrenheit. The reality here is, the lower the return water temperature, the more latent heat transfer that we will have occurring within the condensing boiler. This boiler is made to be corrosion resistant. It can fully withstand the acidity of that condensation. And so we want a low return water temperature to have more flue gas condensation to benefit our COP. We can see here, we start to see condensation occurring at around 130 degrees Fahrenheit. The more it condenses, the more the boiler efficiency will grow. And so we'll keep that in mind when we look at this ASHRAE kind of cookie cutter standard schedule here again. Once again, size 6, 8, 10, 12. If we're targeting an 85-degree leaving air temperature with a commodity standard 2-row coil, we will see a mass average return water temperature of 105 degrees back to the boiler. So not the 140, 120, we're going to see 140 to about 105. And that's going to yield probably something in the realm of, let's say, maybe a 92% efficient boiler, or a COP of 0.92 to 0.93 if we're looking at a full fire design day boiler condition. So,
and that's really fun because often we end up in resubmittal mode on these jobs where we're trying to get the BTUs out of the heating coil, and at the same time the engineer's saying that's all great, but you can't go below 120 degrees. Well, we can't get you the BTUs, so we'll tell you what, solve for capacity or solve for something else, but it's all the same, and we just can't get the heat out of it if the temperature off the coil isn't.
well, and the truth is, once we've assumed a 20-degree delta T, that's going to influence the total GPM for the building we're assuming. It's going to influence valve sizing, distribution, piping. That could even influence, depending on the scope of the project, the nature and the way that we actually insulate pipe. And so when we get that different return water temperature back, it's maybe creating a lot of downstream design work. Now, if we could just start with 110 return water temperature or 100, we're going to have more optimally kind of laid out and designed single duct units. We're going to have smaller distribution piping. We're going to have lower operating costs for the building, and we're going to have a happier owner. So I think the real shift is, let's just assume a larger delta T from the hop with condensing boiler systems. And that would be my advice. If I was the engineer of record, what would I do? I would have more of a 35 or 40 degree delta T for design day.
And if I was a consulting engineer, I'd be yelling to my boiler guys. Are you going to release the boiler at the end of this? Is that going to be the big surprise?
I wish. Unfortunately, that's out of scope for our manufacturing right now.
Too bad.
Okay, so I'm already seeing a couple answers from a few people in the chat here responding, but I'll leave a little bit more time and I'll ask the question, what's the supply and return water temperature that will have the highest boiler efficiency? 140, 120, 120, 100, 140, 90. What are we going to see in this case that's optimal? And so I am seeing a couple C answers in the chat, a few more here. And exactly right, we're going to see the highest boiler coefficient of performance in this case with the lowest return water temperature. And so this kind of leads to the discussion of waterside delta T. And how do we actually increase waterside delta T? But before I jump to there's a couple other really good questions in the chat that I want to address quickly. And I'm seeing a lot of questions now, which is awesome. We might not be able to address all of them live, but you'll have my contact information at the end, and I'm happy to answer any questions or pick up the phone if you want to discuss any of this in more detail. A question from Chad: what's the lowest flow that a box can be balanced to from a GPM perspective? And I'm seeing a hand raise from Tom. Tom, do you want to weigh in?
I think the lowest you can put in is 0.3 GPM.
0.3 GPM is the smallest size manual or automatic balancing valve that we see manufacturers make. So even if we put in 0.2 or 0.1, if we approve submittals, if it goes all the way through, the build team starts building, it's a 0.3 GPM box. We cannot balance the box lower than 0.3 GPM. So that's the absolute minimum. Now, my minimum recommendation from a single duct heat exchanger perspective is actually 0.33 GPM per circuit, which sounds like absolute nonsense. And I'll dive more into that in a little bit here. But that's involved in trying to make sure our fluid is turbulent through the coil, which yields the highest rate of heat transfer. If we get laminar orderly flow through the tubes, we will see heat transfer efficiency drop off very quickly, which we'll discuss here actually in this next section. One other comment from Jonathan talking about the typical 85-degree per ASHRAE 62.1 supply air recommendations. The question was, what's the max DAT we can actually typically achieve if we look at 140-degree water? And I would say 95 is possible, but I would recommend 90 as an upper limit. I prefer 90 from 95 with 140 when we just look at how constrained we can get from like a fluid pressure drop perspective, especially with smaller box sizes. I say 180 can do 95, 140 can do 90. When we get 120, we're pushing it at 90, and I really like 85. If we're below 120, 85 is the way to go. Tom, comment from you, but you're muted.
Do we have a minute I can share, I have a video from my last presentation just about distribution of air at 85 degrees that reduced airflow. I can just share my quick video.
Love it.
Yeah. See if this is going to work. You seeing what I want you to see here?
Yes, sir.
This is 85-degree discharge in a VAV system at 50% reduced airflow. So we just got to be careful with bumping our supply air temperature up. So we're not actually doing a whole lot of mixing here. So this is at 85. This is probably that 50% reduced airflow compared to the 200 CFM 8-inch diffuser. 100 throws not really there. We get a little bit of dropping and mixing. So if we elevate the temperature up to 95, we're going to be stratifying significantly more. So that's just the one point where we're saying, hey, let's sweet spot. 85 is the real sweet spot. You have to really solve your BTU calc. But let's do it maybe with higher airflow diffuser, not higher temperature out of the box.
Strong agreement from me. I actually think 85 from an ASHRAE perspective is maybe a little generous to the design engineer. And really, we'd like even lower than that in some cases. But let's leverage what kind of ASHRAE 62.1 and 90.1 indicate to us. I personally would, if I was the engineer of record, I would be assuming a max of 85 for leaving air temperature, just to really help with the mixing and the air distribution side. So we've talked about why we need a lower return water temperature back to the boiler. But of course, when we think about the boiler's supply air temperature, that's not set by the single duct. That's set by the heating needs of the building. We're existing with 140 or with 120 or whatever it may be, and we want a lower return water. So that really means we need to increase the delta T to get a lower return water temperature. And I want to talk a little bit about how we can do that. And so historically, there was two options. We could increase fins per inch, and increasing fins per inch means we're going to have, looking at a width cross section for on screen here, we're just going to increase the number of aluminum fins in each kind of inch segment as we move from left to right across the coil. Now, this is a well-utilized, well-leveraged product option and market. We have standard coils, which are 10 fins per inch, and all commodity manufacturers have a high capacity coil, which is 12 fins per inch. This essentially just makes a larger effective surface area for heat transfer. For anyone who's familiar with the log mean temperature differential capacity equation, we're increasing our UA. So how much material and how much heat transfer surface do we actually have? Now, this is great because we can get a higher capacity or air temperature, or more importantly, in the scope of this conversation, we can get a larger delta T and less fluid flow. But there is a downside, and that is an increase in air pressure drop. The other option that would be available to us would be oversized casings. And this is the one that I prefer. This is my preference. This is the one that I would lay out if I was the specifying engineer. And the thought process here is, let's step up the coil and casing size of the single duct without changing the inlet size of the single duct. Here, we're going to get, once again, that larger delta T or less fluid flow rate, but we're also going to get lower air pressure drops. So that's going to help with our fan energy index and the fan efficiency for the system. The one downside is we are going to get larger downstream ductwork, and the cost of this option is a little bit higher than, let's say, like a high capacity coil, because we're making the whole product a little bit bigger. And just for scope of that, how much bigger is it actually getting? Well, we're always stepping up one commodity size of casing while holding the inlet the same size. So for a small box, it's kind of like 25%. We have the one outlier of the size 16 stepping up, which is really only like 23%. But generally, we're kind of living in a third to a half as roughly how much bigger we're going to be able to get that heat exchanger. And this option is important because the alternative, which I see happening from design engineers in a lot of cases, is just oversizing the whole VAV box. And that is not my recommendation. I think that's something we need to try to avoid as design engineers, because it can be kind of problematic. The reality is, if we make the inlet bigger, it just means the damper is going to have to be more shut. So a more closed damper means we have less functional damper range, less movement to that damper, which means we're going to have less turn down and control. Lower velocity means lower velocity pressure, which means potentially less airflow measurement and control stability. That can also be a problem for electric coils, which we've been discussing in the chat in some context here as well. So if we need more capacity, if we want a larger delta T, let's not oversize the VAV box. Let's actually use an oversized casing instead. And this is not just a price specific option. There's market competition for this. It's pretty common in market across the board now. Although feather in our cap, we are happy to say we were the first to do it, which I think is often the case. So what I'm looking at here is, once again, our typical kind of schedule. But what we're looking at here is a 140-degree entering water temperature for supply water temp. And what I want to look at is, how does it work if we use both of these options together, which is another big strength. The real reason why I like to pull this up is this is kind of the best case scenario coil configuration we currently have in market. Historically have had in market for low hot water supply temps. And so 140, this is a beast of a box. It has plenty of heat available to us. And I like to call out, when we pair oversized casings and high capacity coils, we actually get a reduction in air pressure drop still. The effective surface area increase is greater than the added resistance to airflow we see from the increased fins per inch here. So in this case, a large delta T of 40, good boiler COP, this is a beast of a box for 140-degree supply water temperatures. But the question would be, what if it's lower? And lower supply water temperatures, of course, can be from that air source heat pump or water source heat pump or ground source heat pump. It also can just be from wanting to run a boiler at a lower hot water supply temperature to get even lower return water temperatures to get even higher boiler coefficients of performance. If we want a 98% efficient boiler, we need to return a 60-degree temperature to that boiler. Functionally, I don't think there are any boilers that are actually operating at 98% anywhere, but let's say we want to yield like a 95% or 9.95 COP condensing gas boiler. We probably need 120 return water temperature to really, or a supply water temperature to really drag that return water temperature down. And so looking less than 120, this is our same fully optimized coil. The one we just looked at, the beast of a box, the best that we've had historically. How does it operate if we have 110-degree supply water? Unfortunately, not good. In some cases, the performance isn't too bad. From a fluid pressure drop perspective or from a fluid flow rate perspective. But for some of these larger boxes where we need more heat exchange and more capacity, we're starting to see fluid pressure drop creep up, GPM creep up. And the reality is the mean delta T for these coils is too low. An 8.5-degree delta T is not providing the coefficient of performance for the boiler we're really shooting for with this low hot water supply temperature target. And so what is the alternative?
There's such a diminishing return on bumping GPM when you're tight like that.
Absolutely. We're looking at what I would consider and call coil saturation. If we were to look at a curve, I'll draw it quick. Hopefully it doesn't look too bad. But when we look at GPM on the x-axis here, and if we look at capacity on the y-axis here, I'm not going to even be able to write those legibly, so we won't see it. What we kind of see is, this shape of curve, and what I kind of consider this top end to be, that's coil saturation. Eventually, we're adding more GPM through the unit, and we're not really getting any improvement in capacity at all. All we end up seeing is super high fluid pressure drops and big distribution pipes and a lot of first cost for really no benefit. And so, just to flip back for context, we had the 2-row oversized casing high capacity coil. What we might see instead would be a 3-row coil. And when we look at a 3-row coil, performance is a bit better. Fluid pressure drop is lower. We like that. Fluid flow rate is low, but we're going to start to see that air pressure drop for the coil creeping up. And I don't love the idea of making the boiler efficient just to shoot the air handler in the foot. And what we're seeing in this case is, yes, better hot water performance, but we're seeing a fan energy index that is getting worse and worse and worse. Once again here, the delta T is still not even that significant. So the question is, do solutions exist? And of course, we talked about new products. So this is me getting to new product and transitioning to that. When we look at a 180 supply system, it's a 1-row coil. When we look at a 140 system, it's a 2-row coil. What about the 130s, the 120s, the 110s? Well, no. I don't think there has been historically a good solution, but we do have a new low water temperature coil. And that's the solution that we would propose makes the most sense at this point. And of course, the next question, the natural one is, what is a low water temperature coil and how does it work? And so I want to look at the scope here of a standard 2-row coil to a low water temperature coil. This is an even more fun exercise if we have the actual samples in front of us. So I've kind of drawn a few graphics on screen to discuss this and disclose it a little bit. The first thing I want to note is this is automatically and always an oversized coil. There is no point in doing it with a standard small commodity sized coil. To really fully leverage the capabilities of this new option, the coil needed to get bigger. So oversized casings are inherently the option that we're recommending here. But the other big piece is the coil circuitry. And coil circuitry is something that I think is not really marketed and educated to the consulting engineering firm and industry, at least from my scope, all that well. And what it really is, it's individual paths that the fluid can take from the supply connection to the return connection through the coil. And so we can see some commodity traditional 2-row coils on the left. And I'll draw a little bit on here too. What I want to note is we have water that's kind of shuffling through all the tubes and then going out the return here. And so when we have a 2-circuit coil like we'd see on the top of the screen, it is almost like two little heat exchangers within one housing and casing. And when we see a 3-circuit coil on the bottom, it's almost like 3 little heat exchangers within one terminal casing. What we're doing with the low water temperature coil is we have actually changed it and reduced the circuits to optimize the amount of temperature we can pull out of that tube, pull out of that coil. So this is a reduced circuit oversized coil. And what that means is if we have 4 GPM in the bottom left coil, we have 4 GPM in the bottom right coil, the one on the right is going to have a much larger delta T because that 4 GPM is transferring energy with air for much longer. It has more tube to travel through. We're going to pull more energy out of it. The delta T is going to be much larger and more optimized at that point. And so what does this actually mean for us? Well, we'll look at performance quickly here. This is a slightly different version of it. This is a size 8 single duct only. We're looking at 120 degree entering water temperature, targeting 85. And we're looking once again at that 50% reheat consideration here. But in the scope here, what we can see is we're going to have our delta T increase. So we're existing at 30 instead of a 2-row coil, which is kind of at 15 in this one performance target I'm looking at. We're getting essentially 3-row coil performance on the water side, but at 20% of the air pressure drop and also at a lower cost. So when we look towards systems and where we need to implement a 3-row coil, the thought process is let's go for a 2-row low water temperature coil because we're going to have lower GPM, a larger delta T, and much lower air pressure drop. Now we're suddenly able to both improve the boiler efficiency without totally shooting the air handler and fan efficiency in the foot. And so looking at this in an even more extreme condition here, what I'm targeting here is a 90 degree leaving air temperature, both for the new coils and the old coils. We can see that here. We have 115 degree supply water temperature, so even a little bit more aggressive. And that discussion of coil saturation that we just had, with a traditional single duct coil, we reach full coil saturation at this design condition. We can see we're pushing as much GPM through this coil as we possibly can. Our fluid pressure drop is astronomical, which we do not love. And our fluid delta T is absolutely tiny, which is terrible for the boiler. The new low water temperature coil is going to operate much better with a much larger delta T. So we've shifted from 3.8 to 17. Our fluid flow rates have greatly reduced from up to 9.5 and 10 down to 1 to 2 to 3, very typical. And our fluid pressure drop is also, because of that lower GPM, at a much more manageable condition. So this comparison here is more of the traditional single duct 2-row to a low water temperature 2-row. But this is kind of the paradigm that I envision a lot of design engineers are seeing. We schedule 2-row single duct hot water coils. We have a aggressive hot water supply temperature, and it simply just doesn't work. So I'll pause there for some questions because we have another transition here. Tom, any commentary from you on that front as well?
If you go back to with the one more, yeah, it doesn't seem super intuitive. On the left, you've got your multiple circuits. Seems like you'd get more heat out of the box because you've got your high temperature coming in 3 different places. So you've got more high temperature. So this is probably that I'm glad you asked that question, Tom, because it seems like you'd get more. Certainly I had, when I've been putting this information out, I called it multi-circuited coils was what we're getting. We're getting rid of circuits. It seems counterintuitive to me. Maybe other people feel the same way. Maybe I'm the lone knucklehead here.
Well, it is a good question, and it is a great opportunity for discussion. And I'll give my pitch on circuits, which I think is maybe some additive context. So when we look at a circuit, an individual path for fluid to flow through the coil. What we're going to see circuits having most influence on historically, or for most products, so a fan coil or a custom coil, why are we going to want more circuits? We're going to want more circuits because we want more fluid through the coil. Every tube has a maximum tube side velocity that we can actually push fluid through those tubes. And what we'll see for heating is about 5 feet per second is about the maximum tube velocity that we can reasonably push through an individual tube. So that equates to about 3.8 GPM per circuit. And so what we would see is if we've kind of gotten up to 3.8 GPM and we still don't have enough heat, we're going to need an additional circuit so we can push into the 4 and 5 GPM up to about 7.5 GPM. Then we're going to need, once again, an additional circuit to get up to, 8, 9 GPM.
But you're compressing the area of the coil every time you add a circuit, right?
Exactly right. So every additive circuit is more fluid, but the actual individual heat transfer or heat exchanger is kind of becoming smaller and smaller and smaller. So there's also diminishing returns on that end. Now, what we're seeing with this reality and paradigm instead is we're seeing the total tube length grow. And that's really what we're trying to get as a benefit here. If I have 4 tubes versus if I have 8 tubes, that's 6. So we'll do 8 tubes. If I have double the tube length and if I have equal GPM, so the biggest consideration, it's the same fluid flow rate. If I have 2 GPM traveling through 4 tubes, and if I have 2 GPM traveling through 8 tubes, the 8 tube version is going to have a lot more temperature drawn out of the tube because the fluid's inside of the heat exchanger for longer.
So this is the condensing boiler of coils.
It's the condensing boiler of coils, kind of. And the important thing to know is how much capacity do we need for the zone? From a fundamental perspective, if we think about the sensible heat transfer, air side and water side equations, a certain GPM at a certain delta T equals a certain CFM at a certain delta T. All we're doing is taking that hot fluid and moving that energy to air, we get hot air. So what we see with these types of systems is we really want to live in the 2 or the 3 or the 1 GPM range. And so we've optimized the coil with all of those considerations in mind. This is a massive system of equations where, all these different elements push and pull and play with one another. But the beautiful thing is we get our little playground for nerds in Winnipeg where we can actually test all this stuff, practically speaking. And, it's not a 1 circuit coil for every single option. It's just less coils than the standard. So some commodity single duct coils used to be 6 circuits and still can be 6 circuits. And some of those might be 2 or 3 from us instead. We're essentially just trying to recontextualize coil circuits to really deliver the goods that this system is needing.
Cool. So good news for all of you. When you pick your V80 box, you're going to spend more time picking them. No, that's not
beautiful thing, I think, is you can actually specify this the same exact way. And it's a drop-down option for us in our software. Of course, we want to give engineers tools to fully understand and get the context of our performance too, but it really doesn't change much besides the oversized casing. So I do want to put this into context a little bit. And, this was something I actually prepared for an ASHRAE seminar in Dallas. It is a quick and dirty on paper energy model. So I apologize. I would have loved to have put this in Madison or something like that, but it was content I already had made. It's my energy model and case study on paper. So I stuck with what I had. But I want to talk a little bit about how would this impact if we actually looked at like a full building? How much more efficient would the low water temp coil be? And we can share this PDF. There's a lot of detail in here, and we've had good conversations. So I'm cognizant of time and the fact that we still have one really fun product to discuss at the end here. So I might go through this a little bit more quickly, but I'm happy to provide any context into the calculations, and we're happy to share the slide deck as well if anyone's interested. So my assumption is a high school in Dallas. It's a classic air handler and VAV system. We have a condensing boiler and a heat recovery chiller. And so because of those two things being used in parallel or actually in series with one another was my assumption, what we're going to see is a 115-degree hot water supply temperature. So a very lean hot water supply temperature, something that we could see in Dallas that maybe at this point would be less common in Wisconsin just because of the heating load we actually need to provide to the building. But I'm looking at a few zones of interest. So a classroom space, a cafeteria, a gym, offices, corridors, and a library. And of course, would I actually, as an engineer of record, serve a gymnasium with single ducts? No, I wouldn't. I would use, an air handler as a designated zone, likely if this was the system type I was using, but I wanted more zones so I could get more data. So forgive me for my design mishap here. Of course, it would be a good candidate for a standalone AHU or packaged RTU, but I'm doing VAV boxes because I hold the keys to the kingdom at this point, and that's what I decided. What I have for each of these zones is their square footage, their sensible cooling load requirement, which is based off of an external load of 10.92 BTUs per hour per square foot for cooling, the heating load, which is based off 9.68 BTUs per square foot for heating, and then I did full internal loads based off of occupancy, square footage, electrical distribution, all that kind of stuff. And the first piece here would be actually sizing the single duct boxes. So if we look at a classroom, it's getting one VAV box. Its cooling CFM was about 1100 CFM. So, we size a size 10-inch box for that. When we look at the cafeteria, it's needing 4600 CFM for cooling. So we're actually going to need two size 16-inch boxes in that case. And we can kind of see the process here where I've sized the inlets, I've sized the design day heating CFM requirement, the cooling CFM requirement. And I also want to note, in some cases, the design day heating CFM for this little energy model, they actually had CFMs exceeding 50% of design day cooling. So in some cases here, that would need to be addressed via sequencing. There'd maybe be a need for some supplementary heat in the zone if we don't want to do full heat through the VAV system, but another consideration to flag there. And then this is a really important step. Once again, just kind of math on paper for us here. But the difference between the heating load for the zone and the coil load, the actual coil capacity here, which is a very different constraint and a different performance characteristic for the building. If our heating load for the classroom here is 8.7 MBH, what we're actually going to need from a coil load perspective is 17.6 MBH. And the reason for that is, our heating load is assuming our space temperature is 70 degrees and, the temperature and energy exchange is occurring from a 70-degree space to our outside ambient conditions. While our coil load is needing to actually elevate the temperature of 55 degrees saturated air all the way up to 85. So actually a much higher load than the heating load needed for the space. That's actually a step that I see missed in some plans from some engineering firms. I'm sure that's not from anybody here, but something I would want to consider and throw out, that the coil load is much higher than the heating load for the building in these for each of these zones. And so once again, kind of a review of these zones of interest. and looking at a standard 2-row coil versus the new 2-row low water temperature coil, what we can see is some significant different performance in this case with our leaving water temperature for a standard 2-row coil, being much higher than the leaving water temperature out of the coils for the low water temp coil. We can see a reduction in fluid flow rate. These two things are very linked together. And so that is an unsurprising performance dynamic that we see. Another big benefit here for a significant decrease in coil air pressure drop. So kind of summarizing all these zones together, there actually are 13 classrooms we can see in this little render. There's one cafeteria, but it has 2 VAV boxes. Once again, our gym, which we would do as an air handler, but in the scope of my conversation, I did it with 5 single ducts, which is goofy, but gives me more data to look at. Offices and meeting spaces, we have 2 little offices zoned together, 14 total offices for 7 VAV boxes. The list goes on. For these 33 total VAV boxes, we see a 56% decrease in GPM on design day. We see a 13-degree reduction in return water temperature, which we would estimate in the case just looking at some standard boiler efficiency curves. This improvement in delta T actually yields 4% better boiler coefficient of performance. We're seeing a reduced maximum air pressure drop and an equipment first cost of about 15% higher. So the one thing I'd note here as well, and I have kind of a last, once again, on paper, simple energy and payback analysis discussion here. But what we're going to see just from a boiler perspective, just looking at that 15% increase in equipment cost with some kind of standardized assumptions for margins, both from the point of sale and the contractor, we'd still expect in this case just the system efficiency improvements leading to payback within 2 heating seasons. Now, there's also first cost savings like smaller pumps, smaller distribution piping, smaller valves, that this is actually cost saving off the hop. But all of that removed, the payback period would still be very quick. Also, in a market where heating is really not a significant, as significant in Dallas as it would be in a market like Wisconsin. So I want to talk a little bit more about some of those first cost savings, but it's actually better to do that in the context of this final new product discussion, which I want to have on our new Aris single duct unit. And this is kind of the last piece of the presentation here. And this is the privileged look where this is kind of the first en masse marketing of this product. It's one that I've been working on for quite a while. And so excited to hear feedback, would love, follow up with emails or shoot, me, Tom, an email, anyone from the Airflow team. We'd love to hear your thoughts on this as it's kind of pre-release, targeting a release in March of this year. But it's a single duct unit that we've branded and called the Aris. And I want to talk a little bit about why this happened and why it occurred and how we got to this point. And I think the real important context has to do with the Center for the Built Environment out of the University of California, Berkeley, University of California, Berkeley Center for Built Environment, they are really one of the most forward thinkers from a research perspective on buildings in operation in the United States. And I would even say globally when we look at HVAC and the built environment. Their intent is to really take the pulse of buildings in operation. So they measure building performance, performance of different systems within the building. They measure and kind of catalog and categorize occupancy responses to some of these changes that they institute with their studies and research. They want to improve indoor environmental quality, and they want to improve system efficiency to be more environmentally friendly. And so we can see I pulled some of the HVAC things that they've done over the last couple of years, significant research comparing hot water and electric reheat. These two we really like here at Price because all of the testing actually happened in our facilities. We can see underfloor air distribution design guidance. This is in a room that I spent a lot of time in, our mock-up room in Winnipeg, Manitoba. Lots of things on decarbonization and heat recovery. And so they're very much a forward thinker. And they engaged with us in 2022 to come to Price to do research on VAV reheat systems in particular. And I was kind of in charge of, being their Price representative for all of this research and testing that occurred in 2022. And the scope of this, this is a publicly available research paper that's quite a good read. Their concern was, do VAV boxes work at 120 degrees? Are they going to continue to work at 120 degrees? What if we want to retrofit a boiler into a building that has old coils? Will the building still work? And they found some really cool, interesting key findings. The first was, which we can see on the right-hand side of the screen here, they found that coil capacity drops by 13.4% when the damper is only 27% open. So I'll give some more context to that, but let's try to mentally digest that. As the damper shuts, the coil gets worse. So we can see that here on the x-axis, capacity when the damper is 100% open versus capacity when the damper is 0.27. We can see a huge deterioration in coil performance. They noted a big risk of temperature stratification. So sometimes with that mixing element being a damper, directly upstream of a VAV box, we're going to get a lot of temperature stratification downstream, which could be problematic for single point discharge air temperature probes. And what they really proposed was we need to continue to revisit and improve static pressure reset sequencing on buildings. We should use averaging DATs. And then they really kind of left this as an open-ended question saying, which manufacturer is going to make a product that works better for this? And so that was the scope of my work. It kind of is when my wheels started churning, and we started to do some independent testing at Price facilities, trying to further quantify and understand what is the impact of a damper on a single duct reheat coil. And what we found was very similar findings, up to a 15% degradation in capacity when a damper becomes too close. And the problem here is we could use static pressure reset, so essentially turning down the air handler to make dampers more open to kind of rectify and overcome some of these constraints. But the truth is, even with static pressure reset, we still generally see dampers in fairly closed off positions. This is from an ASHRAE study looking at an office building in California, and they were measuring the typical damper position during intentional reheat with static pressure reset. They still found the bulk of the time, the damper was 40 to 60% open, so in a fairly closed position. So what we've done is we've created a new product. It's patent pending. It looks very much like a normal single duct box, intentionally so. But what the Aris does is it just recontextualizes and repackages the major components to overcome this design issue. And what we've done is we can see here, we've moved the damper downstream of the heat exchanger. We've moved the heat exchanger up to the front end of the box. And we've still maintained the cross-flow sensor in the inlet portion of the unit, which is really critical to make sure we measure and control airflow properly. So what is the result of this? Well, we can see the Aris in black here versus a commodity kind of traditional single duct unit in blue. As we move with a constant airflow through a variety of damper positions from 100% to a test point that's at about 65 to about 45% and down to a minimum of about 30%, we can see the Aris product maintains its heating performance, and actually, because of back pressure, it gets a little bit of a boost as the damper gets more shut, where a commodity traditional single duct is going to continue to have that performance deteriorate as the damper gets more and more closed. A question from an attendee: does it increase the VAV box length while having a damper downstream of the heating coil? Yes, about 3.5 inches. So our original design, which you can see was filed for patent in the top right, actually maximized this length a fair bit more. But the latest version of the product, which we can see here, really minimizes it, because we found we still got about 70% of the performance improvements by close coupling the inlet to the coil. So not fully optimized, but trying to package it more like a typical single duct unit, because that's great for consulting engineers. It's good from a cost perspective. It's good for contractors who are used to seeing VAV boxes in a traditional size and shape. So this last graph was looking at a constant airflow, but we also went above and beyond the scope of the testing from that CBE study, because I really wanted to look at this in a more dynamic real world operation. And what I wanted to see was, how is this going to work with a variable airflow rate? Because the truth is, 50% reheat to 100% maximum cooling, that means the damper is going to be partially shut already. And what about part load conditions where we expect that airflow to reduce to 40 or to 30 or to 20%? How's that going to influence the greater operation of the product in this case as well? And so what we can see here is the Aris single duct with the damper downstream is consuming on average 70% less fluid than the version with the upstream damper, while targeting the same capacity and leaving air temperature, which in this case was 90 degrees, looking at 120 degree entering water temperature. So throughout the range, throughout dynamic operation, we're going to see a lot less fluid moving through the system. So pumps that are happier, larger delta T's in dynamic operation, and therefore a higher net typical boiler COP. I'll pause here for a couple more questions I'm seeing in the chat, which I love. Thank you, and looking forward to hearing more feedback on this as well. One question was, does it increase the bypass through the coil as well? So I'm thinking we're discussing kind of like airflow bypass through the coil. And all of the testing that we have done is assuming the same supply airflow rate at the inlet, targeting the same capacity leaving air temperature. We actually have CFD analysis on the product that is going to be finalized by the end of this week. That might be able to pull back the curtain on that a little bit further. But broadly speaking, I would say no, at least not to a point that it would impact performance that's measurable in a lab. I did see here from Matt, how's the configuration of the integrated actuator and valving setup with an inverse box like this? So one other thing I'd like to note here, the original patent drawing here is not representative of the final assembly. What we can actually see for this product is, I'll draw the control box here. A control box for a traditional single duct would exist here. The control box for the new single duct would exist here. It's shifted slightly, but it's the exact same size, has the same clearance for DDC controls to be mounted, and is still in the same orientation, right hand, left hand, top or bottom, depending on however a design engineer designs it and a contractor purchases it. A question from Ryan, how does this change access to the coil for cleaning and maintenance? That is a great question. We do have standard access doors downstream, and then we're also going to have an upstream access door section that will slightly bump the assembly out if an upstream access door is also required, which is a consideration, but we've tried to make the base box as cost effective as possible. So that was a big desire and need for us there. A question from Heidi, why does moving the damper mean less fluid flow? And so the importance here, and I'll kind of go back here to answer Heidi's question, as the damper gets more shut in a traditional single duct, it's essentially casting a larger shadow on the heat exchanger, and we're going to see airflow hit the top and hit the bottom of the coil. When we move the damper downstream, we're going to get that main mass, and I'm going to remove some of the ink here. the main mass of air is going to go right through the middle of the coil. It actually spreads a little bit as it travels through. And this is true independent of damper position. And that's the big influence there. More effective usage of the coil surface area, and therefore a greater heat transfer, which means less fluid flow requirement. We're going to continue here with a couple more product considerations from a performance perspective. From a cost perspective, I do want to note, the target here for us is to have this as a commodity product at a commodity price point. We envision this being used in lieu of 3-row coils in a lot of considerations and times. So this is priced on average, identically to a traditional 3-row coil and box. So no, we're not doubling the price of the single duct unit. That is not the intent. My major consideration when, being part of the development team for this product was knowing that we're a commodity product manufacturer and existing in a commodity market and wanting to provide this as a service to the industry and to grow our, maybe base of design market share, but not to suddenly make single ducts twice as expensive. So a consideration there. From an air pressure drop perspective, a 3-row coil would be highest air pressure drop in black. A traditional commodity 2-row coil in teal. We see the Aris with an oversized 2-row coil coming in a little bit lower, and an oversized commodity 2-row coil being the lowest. Generally speaking, though, my recommendation is to exist below 2,000 feet per minute, which is 700 CFM for an 8-inch box. And we can see the difference between these two is much narrower. Another good rationale for not putting too much airflow through a box inlet. Another great byproduct here, the reduction of temperature stratification. So we can see with a traditional single duct box, this kind of blue band that carves through the middle when we look at temperature stratification and kind of lack of mixing. The more closed the damper is, the harder it is for that hot air to have immediate access back into the center of the ductwork. All of this is measured at 2 feet downstream of the discharge of the terminal. And if we think about putting a discharge air temperature probe at a single point, it's possible we could be measuring 82 degrees rather than a mean temperature of 90. It's possible we could essentially be measuring a temperature greatly different than the average temperature being discharged out of the product. Another thing that the downstream damper actually solves in this case becomes a bit of a mixing element after the coil to help reduce that reality. And then there are some great potential first cost savings. So of course, with fluid flow reduction, we're going to see smaller temperature control valves, balancing valves, and strainers, smaller distribution piping and pipe insulation, the potential in some cases for smaller boilers. Not in all cases, that would depend on some specific boiler selection fundamentals. We are going to see a smaller fluid pressure drop for smaller pumps. We're going to see also a nice benefit of this, potentially a round duct connection. We have round and rectangular slip-in drives, both as standard on the product. Something I like to note, spiral duct is much lower leakage than rectangular duct. And when we think about a low pressure ducted system that is generally not being tested for leakage, that is generally kind of a blind spot for the system, I really like the idea as a consulting engineer being able to specify spiral duct that I know is going to be lower cost for the owner while also being lower leakage, potentially helping with operating costs and thermal comfort as well.
See that one coming in the downstream side. Nice job.
Yeah, no problem. And so I've gone overtime. I have. I did not leave a ton of time and conversation for the Excel toolkit, but my last thing I want to note, it's 2 slides. What are the adoption challenges and what are the scheduling recommendations? Well, back to early in the presentation, do I expect HRI 410 or 880 will quickly catch up with this product? Unfortunately, no. I don't think we're going to see the standards modified at the pace that manufacturers can release new product. That is for sure a consideration. Another one, engineers will want to specify products with market competition. Yes, I understand that and I agree. Um, and that is a consideration as well. So I think from our end, we're going to view other manufacturers seeing this product and probably coming up with their own version of it. We generally patent because we like to protect our IP from a we were here first perspective. But I'll tell you, we had patented the crossflow sensor for a single duct, and that patent was live until about 2 years ago. We've seen crossflow sensors on every product in the single duct market for a long time. We don't make money from suing people. We just like to say we were here first. So undoubtedly, someone will come out with a competing product to this quickly. But until then, how could we leverage a product that maybe improves system performance while allowing competing bids from alternative manufacturers? I would recommend really just this one note here. And this would be something I would love feedback on from the group. If you have thoughts on a different approach, shoot Tom an email, shoot me an email. But what I would suggest is specifying and scheduling that the water coil must be tested while integrated into a single duct unit with a damper position to 50% open. That just means you're going to get straight goods from everybody. I think it's simple. I think manufacturers will have to conform to that if it's specified. And, if their product can manage that, then great. And if it deteriorates coil performance 5%, then great. It'll be accounted for as well. Our vision is that we will be able to provide that data for all of our traditional single duct units as well. And we're working on compiling that data now. And then we also have a product that solves that problem. So that's kind of my last closing thought and comment. With that in mind, that's the end of my scope of the presentation here. I did not leave a ton of time for Suthan, which I apologize for.
That is okay. There's a couple of questions in the Q&A about acoustical performance, which I suspect there's a few people concerned that the downstream damper will be loud. I don't
Yes.
know. I suppose it could.
Yeah, it actually, so really notably, it is a bit louder than a traditional single duct. And we have all the sound data for it. It's actually going through right now, like we've done testing on the 6, 8, 10, and 12 for acoustics already. And the rest of the product line is actually testing in the month of December. We're targeting a public release for this product in March. So timeline perspective, that's kind of where we're at. We do see some sound increase because the velocity through the discharge is higher. And the reality is it's not 10 NC, it's not 6 NC, it's an NC point here or there, which we discussed, how are we going to rectify that? Later in the summer, in around July, we're going to be doing the full silencer, like a SDVQ option. We're going to have our attenuator option to allow this box to be configurable from an acoustical perspective too. So if that's something you specify and are used to seeing from Price, you'll see it on the Aris as well. The other reality is the box is still quiet enough for typical operation. It's still quieter than a lot of our competitors' equipment. So is it louder? Yes. Absolutely. We're not shy about that. I still think it's plenty quiet enough for traditional built environment occupied zones.
And if we can be totally honest about it, it's how much pressure drop that damper eats up is really the driver of sound, not the fact that you have 12 inches of insulated cabinet that's protecting the box plus the coil. It's really how much, the difference between a half-inch pressure drop across the damper and an inch is colossal. So
Absolutely
that's
right.
when you're looking at attenuators, not so much hey, I've got this much terminal box after the damper that's going to really protect it. And there's some, but not a ton.
You're dead right.
Yeah.
So
Suthan is going to quickly introduce you all to the Excel plugin tool and do a couple of quick examples. Now, the new terminal box data is not in that software yet. However, it would be a great idea to practice because the moment that this becomes available, you're going to want to know how to use this tool so you can upgrade the performance of your terminal boxes. And Suthan, quick intro. Suthan's been with us. Well, you can do your own intro. In
Sure.
fact, they made you rehearse it, so let's do that.
Hi, I'm Siddhan Nair Prakasha. I work with Airflow for 2.5 years approximately, and I work with Engineered Channel Group. Um, Thanks, Mark, for all the presentation. It was a lot of information, and I will try to run through this as fast as possible. Um, so right now we are going to go into Price Engineering Toolkit, which you guys can find it in Google. If you guys can Google Price Engineering Toolkit, this is the landing page which you guys will land into. And um, before I tell you how to download and stuff, like this engineering toolkit does basically solve like two big issues, which is like time wasted on submittal reviews and inaccuracies in performance data and stuff when you guys are selecting VAVs. So in order to rectify all those stuff, this engineering toolkit definitely boosts the performances and efficiency of your workflow for selecting VAVs though. So this is the landing page for the engineering toolkit. And right now, today, we are just going to talk about the Excel toolkit here. And there is Revit toolkit, which is pretty amazing, but we can have that topic for some other day. Or if you guys can reach out to me or to engineering at Airflow Reps for more questions related to that. So in this landing page, if you guys click the Excel toolkit, it takes you right down here to download Excel toolkit. And this automatically directs you to the Microsoft App Store. And if you guys click Get It Now, and you guys will have Open in Excel tab in the next page. So that is how you download this plugin tool, which is for Excel. So once that has been downloaded, all you guys have to do is open Excel. So in Excel, where you guys will find this price industries tool is going to be on the top up here on the toolbar, which says price industries. So if you click price industries here, you guys are going to get all the parameters related to price industries, which is the competitor cross-reference product line to their direct price industries website, and few other products which we can use this to create a schedule, which is a dynamic schedule. So how they do this is a cloud-based solution to create a dynamic schedule with real-time price industry performances though. So these are not preset calculations that is there in Excel, but they all take the data from the cloud. So whatever they update, it's going to get updated in this toolkit as well. So as Tom said that it's the new low entering water temperature is going to be in Excel probably in next month or so, I guess. So right here, when you guys have this tool for selecting, for example, we can do a single duct unit for now. So when you guys do a single duct unit, click on single duct unit, and if you guys go to create schedule, it's going to ask for two different parameters, and which the first one is going to be your reheat type, which can either be a water coil or an electric coil. So let's assume I'll do a water coil today. So water coil. And the second thing is the solution method. I know a few people have different types of solution method they want to try to solve with. LAT is usually optimal for the occupant thermal comfort. And usually I think a lot of engineers prefer to go with the capacity. So I would run with the capacity. And here in acoustics, when you are creating a schedule, if you guys want the noise criteria and sound power level to be in the schedule, you guys can have that right away in here. If you can pick the NC and sound power, or you don't want the NC at all, click none. So I'll throw in NC for now, and I would click generate schedule. And here we have a blank dynamic schedule, which we have to fill in a few parameters in here to get the performances of a particular box. So right from the top here, the single duct default, these are all default parameters, which is going to be in a particular building. It's not for a particular VAV box, but it's for the whole building, which is you can allow below minimum airflow to be true or false. You can have just even sizes, your fluid type water, what is the glycol percentage. This is your industry standard traditional values, primary at 1055, return is 75, and you're entering water temperature, which is 140 degrees or 160, 180, depending on what you guys have. So right here, we have got few different cells, which has three different colors to it. So the blue cells are the ones that we are going to input our parameters. Your orange cells are going to be the calculated cells, and the green one is, I would call it a optional manual input or an override cell, which is only on the unit size, because I've seen a lot of engineers who wants to have their size, like if it's a size 4, I can do get a performance from a size 4 VAV box. They would still put in a size 6 in there. So that's why we have it as an optional manual input or an override cell. So let's run with an example. So VAV1, and here I can have the cooling minimum as 500, cooling max is 1000, reheat at 500. And these are your industrial traditional standards as well, the static pressure and the downstream pressure. And you guys have the options to pick all this discharge attenuator, liner, and silencers. But when you guys see here, there's multiple different FF1, FF50. Like, it might be hard for you guys to figure out what these liners are. That's when the single duct legends here can give you all the information about what are these liners, what are the descriptions about all the different parameters here. So use that to know what type of liner you guys want to pick, and just picking up. So right now I'm picking a 1/2-inch fiberglass, and over here for the casing, standard or oversized, which Mark just spoke about. The standard is the normal standard casing. The oversized casing is basically to accommodate oversized coil, which reduces pressure drop by increasing the face area, and but you don't have to sacrifice to control the low airflows as well. So on the coil capacity, we also have high capacity and standard. Same standard is 10 fins per inch. Your high capacity is 12 fins per inch. So I'll pick standard, and I'm going to start with just 2-row coils for now. And once I'm done, so I selected heating capacity, the heating solution method to be in capacity. So I will throw in, I want to have like 10 MBH. Once you plug in the last parameter, you can see that it automatically calculates all the necessary parameters needed here though. So you can see the sound power NC, which is 25. And so you can still use all the Excel rules here, like these blue color cells are blank cells. You can still use your rules to have multiple different CFMs listed below here, or you guys can create like 10 or 20 different VAVs at 100 CFM, like 500, 600,000, 1,500 to know what exactly the values are. So for example, here right now, it says 1,500, it says the unit size is 8. But if you guys want a unit size 10, you can still manual write it to 10, and the performances changes accordingly for the unit size 10. So this is one way. And where do you guys find the model? Models are going to be listed here. SDV low profile, and the quiet box are going to be here. So this is how I usually do my selections, and it's kind of pretty neat for selecting faster all the VAV boxes, and I can do pretty much like 100 selections, like matter of like few minutes. If you guys have like fan power terminal boxes or fan coils as well in a particular job, you guys don't have to save this and create a new Excel sheet or something. You guys can just go here and create a fan powered, create schedule, and give standard, reheat type as water. I'll calculate with fluid flow and generate schedule. It's going to create a new sheet here for me with a fan powered data that I need to input here. So I know
a lot of our customers already have an Excel spreadsheet. where they
Mm-hmm.
do terminal box tabulation.
Mm-hmm.
This, how would you integrate this into what they already have?
So they would calculate everything in a theoretical basis. Like, they have their preset equations that they get the heating load and stuff. So what I would do is if they have it in Excel, I would just copy and paste the cooling min, cooling max, and the reheat and all the stuff, and they can get a dynamic performance,
Sure.
which is very close to their theoretical performance, but this is closer to what our practical, price VAV box performs at that particular.
Right.
Uh,
So they're going to port over their tag,
mhm,
cooling max, reheat, and
mhm.
probably MBH. And then
Yes, depending on what their solution method is. Yeah.
and what I think they're doing next is just simply looking for problems from the base solution and going, well, maybe we've got a couple of outlier boxes.
Hmm.
We're not getting capacity in this one, so we're going to bump this to from a
Right.
standard to a high capacity, or do an oversized casing, or what have you.
Right. So for example, if they have done already a calculation, they have a schedule and everything, and then they want to do some changes, they can still go back, just change it. Okay, I need more MBH on my box, like change it to oversized casing and see what do you guys get? Like, what is the parameters that you guys need to improve on that? And if you guys want to just copy and paste 100 different VAVs, and this is the best place to do that. So it's going to calculate all the 100 VAVs at the same time. And later down the project phase, if you guys change something like the reheat CFM has to change, you can still change that once at the end of the project, and you'll get a accurate dynamic schedule though, so which is very helpful. And I have gone to a few engineering firms. I have did a lunch and learn with them, and I've got very good feedbacks on this, that people really love to use it to save time and to get an improved efficiency on that stuff. If you guys really want to know how these formulas still work, you guys can still click on these, and you guys can see that which parameters the Excel is actually taking to calculate and stuff. So, which is pretty cool. And one more thing, if, for example, if there is an intern in your engineering firm and he's trying to figure out things with not a lot of knowledge, if you mess things up, like let me do 1,000 here, and I'll put cooling max is 500, which is not right. So, and my
It looked
reheat
like
is 1,000.
It looked like Mark had something he wanted to add here.
Yeah.
Yeah, I did have one comment. Suthan, I could add it in right at the end, but Tom, I thought you did raise a really interesting point about what if we have a template we already like? Suthan, can I share something really quickly?
Sure, go ahead.
I just had the thought because my team recently did this for a couple different firms. We do have the ability to kind of do a bespoke version of this as well. And so, an example here where we were creating a version for, an engineering firm in the Northeast, BR plus A, who specifies a lot of our fan coils. And we can see here, this is a template that has all of their parameters kind of set up and fully linked in the schedule they like. Another version of this, an engineer on my team received kind of standard schedules from a firm for all their fan powered box or terminal schedules, and we could match the format.
Right.
And
So
so,
instead of using the price plug-in tool as it's the schedule generator, we can work with you to build the price data into your schedule. So if you really love the schedule that you've been working on for the last 15 years, we can enhance it with live data. And as we get more low water temperature and downstream damper, that information will update as well. So we're happy to do that as well. And I know
and
you've already done some of that.
and the thing I would say as well, you probably have at all your respective firms a new grad mechanical engineer who's an Excel wizard, probably.
Mhm.
And likely that Excel wizard is way more capability and capacity than I would have in Excel. And I have seen in some situations firms take the logic from our toolkit from essentially load calculations for heating, cooling, and ventilation loads. They put it all in and they get full VAV box schedules without really doing any design work at all. We have made it to be no guardrails, which is intentional because we like it. We like to envision it as kind of like a sandbox where you can make whatever sandcastle you like. We just have a lot of tools to make it functional out the gate as well.
So for those of you, many who are still sticking around a few minutes after, I just wanted to say, first of all, thanks to Mark for a great presentation. And I've seen this presentation a couple times. It has definitely grown in scope, and it's one of the better ones I've seen in a long time. So since all of you love VAV boxes, fall in love a little bit more. And Suthan, thanks for abridging your presentation for us. And for all of you in the audience, thanks for spending the last couple of hours with us. And next year, we're going to be a little more in person versus all web-based and in our auditorium. So look forward to seeing Airflow at some event near you in 2025. So thanks everybody for your participation. And if we don't see you earlier, Happy New Year. All right. Thanks everybody.